A very good morning to everyone. Today we'll be starting with the difference between how the classical computer works and how the quantum computer works. So we'll be seeing okay, what's the difference between the quantum computer and the classical computer, and do we really need quantum computer or is just the mere the horse race there? Okay, fine. So yeah, okay. So for understanding classical computer, we first need to understand what are the bits. Okay. So let's talk about first about the classical computer and what are the bits. So let's talk about the classical computer. Pardon my bad handwriting. I am a bit out of practice right now, but yeah, I'm getting back to it. So yeah, in classical computers, basically they are transistors, they are processors, and you have mainly binary digits, that is zeros and one. Okay, and using these zeros and one, the combination of zeros and one, you can create using the combination of them, you can create various things. Like using this construct combination, you can specify the instructions, and using these zeros and ones, you can create a decimal number. You know the comparison between the decimal number and binary. Using these zeros and ones, you can create ASCII values. By ASCII values, I means like the character charts. So I'll be showing you the character chart in the next slide, and there you will see that how the binary digits can create emojis, classical charts, etc. And how can we do it? So that we'll be seeing it. So basically, in classical computer, we only have two things like just zeros and ones. And zero specifies in a circuit that the voltage is low, and one specifies that the voltage is high. One specifies that the voltage is high. So if I have a circuit, suppose I have a logic gate, suppose I have a logic gate, not logic gate. Okay. And using this not logic gate, what I can do is if I give it 0, it gives me 1. Okay. And if I give it, as the name suggests, not gate, if I give it 1, how will I will get 0. Okay. So what we see that how these binary numbers do what all the things was I'm doing in my computer. Like suppose if you are programmers, if you belong to a programming background, if suppose you write a Python program. Okay, you write a Python program to check if a number is greater or not. Like if you have to check if 5 greater than 2, then print 5 is greater. Else else print 2 is greater. Well, we all know that the 5 is greater, but that's the syntax of the basic Python program. We write like this and we think that the computer understands the English language. Well, of course not. This program gets compiled into this program gets compiled into binaries like the machine language. This program gets compiled into machine language, and this machine language then executes your program. Okay, so it's not that simple that the Python programmers, the computers just understand the English language, what all the programs you write. The computers understand the compiled version of your program. Whatever the program you write or whatever the instruction you give using graphical user interface or the command user interface, it first gets compiled into the machine code, and then using machine codes mean like the zeros and ones. And using these zeros and ones, this machine code executes the instruction. So that's how the classical computers work. Okay, and we can see a gate which will help me to do the comparison operation. Like let me name that gate as 1. So yeah, suppose we have a gate greater than or equals to 1 gate. That's how I name it. So of course I'm giving this gate greater than or equals to 1 gate first 0 and 0, and then greater than or equals to 1 gate 0 and 1, and then greater than or equals to 1 gate as 1 and 0, and then greater than or equals to 1 gate as 1 and 1. So let's understand what the 0 0 means. 0 0 means in decimal notation 0. 0 and 1's mean in decimal notation 1. How we get this? You must get this by 0 into 2 ki power 1 plus 1 into 2 ki power 0. Here we will get as 2 like 1 into 2 ki power uh, sorry 2 ki power 1 plus 0 into 2 ki power 0, and here we will get as 1 into 2 ki power 1 plus 1 into 2 ki power 0. So that will be 3. Okay, we both know that all the last three options will be true because 1 is greater than or equals to 1, true. 2 is greater than equals to 1, true. 3 is greater than equals to 1, true. So here, of course, we specify that 1 represents true and 0, if we get 0, then it represents false. Okay. So can you think of a gate? So can you think of a gate like if I have A, B, C, you know the gates. So if I give 0 and 0, then is 0. If I give it 0, 1, then is 1, 1, 0, then 1, and 1, 1, then 1. Of course, you might get the answer that the answer is OR gate. Simply OR gate because the OR gate is can be used to construct check whether the number is greater than equals to 1 or not. So you might have not get it by first understanding greater than equals to 1 gate what it is, but after seeing the combination you will find that this is OR gate. So using the combination of all these gates, like if I have, suppose I have a bit n bit, give it to one gate, gate 1, gate 2, and similarly to various gates to get the expected result. What do I want it to? So here we use a combination of gates to form addition, subtraction, etc. And that's why classic computers, you might think that the computer works very fast, but in reality it has to pass through various gates, and thereby it you can understand how many gates we will need to form the complex combinations. Okay, the image you are seeing means what you are seeing means also in bits and binaries. Like suppose if I am streaming this video live on YouTube, how my information, my let me take one other example. First, you understood this now that this is OR gate, and here we are using greater than equals to one gate to specify the result. Okay, now we will see okay, how does the image works. Okay, what happened? Yep. So okay, fine. So like if I'm streaming a video, I'm here, so this is me, and I'm streaming a video to your computer. Suppose this is your PC, and you are seeing this me. Okay, so how the internet transfer the information in packets, like packets by being like zeros and ones, and using these zeros and ones, we are representing the information on the computer. So understand your computer as a row of column. Okay, as a combination of row column, like there are rows, and there are columns. Sorry. Yeah. So this is how it. So suppose your LED screen or whatever screen, computer screen you are using, it's a combinations of all these points as of this. Okay. So let me clear like this is pixel, this is another pixel, and this is another pixel, and each pixel has an RGB value, like red, green, blue value. Okay, whatever the value of it. Suppose if it's 0, 0, 1, then the combination that we will get blue color. So here it will be blue color. Okay. So this is what we see in our screen. Like whatever we see are in the pixel formats, and using the pixel format, the image is constructed. So you can understand like face unlock feature. How does face unlock feature works? The face unlock feature basically maps it for a face unlock feature. Basically, we are giving it to a program. What our program see? Program doesn't see your face. Program is not racist bias or whatever the hell that is. Program just sees ones and zeros, and everybody's face features are different. Like everybody's the positions of nose, the patterns here. Suppose this is node 1, this is node 2, this is node 3, this is node 4, and the combination of all these nodes, like combination of all these ones and zero. Okay, suppose for my face, the ones and zero will be like this: 1, 0, 0, 1, 0, 1, and like they will be. It's like a three. It's like a three dimensional matrix. Yeah, it's like a three-dimensional matrix, and there are I saw told you already that there are RGB values, and using the RGB values, you can construct with pure values, like all the seven values. You just need three colors, red, green, blue, and you can construct the various colors by using different shades of various colors. So using these three graphs, you will specify what's the value of red, what's the value of green, and what's the value of blue. You will be able to construct the color. For my face, the RGB, the pixel value will be different, and for other person's face, the pixel values will be different. So this is how the computer works, and this is how the face unlock feature works. So what I'm trying to tell you that the custom computer heavily relies on only two things, two digits, that is binary one and zero. So one is one and another is zero. So don't you think that at the time will come that we will be needing more than ones and zeros, because at one point how much can we rely on one and zero, and how much can we really use them? So there, that's where the quantum computer kicks in, and to show it before, let me show you first the SKI chart value. uh, 1 second. So yeah, this is the sky set of the values, and you can see that every character, every uppercase character, every lowercase character has its sky value. Like suppose I will be taking like these are the sky values. Let me take my pen. 1 second. Yeah. So these are the sky values of the instructions. Like these are the acknowledgement instruction and the other various instruction for different operations. And using these operations, you can perform various things. And these are the sky values. The sky values see the binary digits. The binary digits for the exclamation mark. And if you just write suppose my name DEV, that in binary will be like D is like 0 1 1 0 0 1 0 0. So let me type 0 1 1 0 0 1 0 0. E will be like 0 1 1 0 0 1 0 1, and V will be like 0 1 1 1 0 1 1 0. So yeah, my three character name which I used will be represented in binary like this. And that's like 8 times 3 24, 8 times 3 24 bytes. So yeah, you can see that how much processing is done here. And if I have to perform an addition like 5 plus 6, then the first 5 will be converted to binary, 6 will be converted to binary, and there will be the operation plus operation will be converted into binary. And using that operation, then the first the result will come in binary, and then it will be converted back into the decimal number. So that's how the thing is done. So you can see that why just zeros and ones? This was a three-letter word. Suppose there was a guy, Tamil guy, not to be racist. I'm not racist like now, like something like that, not stereotypist. So usually Tamil guys have long names. So if he has to write his name, then in binary you can imagine how much word length it will be in binary and how much space will be taking. But 24 bytes is not much storage with thanks to the advanced technology. But at a time we will, as the data is going at a very high exponential rate, at a time we will be needing a more better way, just more than 0 7. For zero, we just it's just like low voltage and it's zero, one high voltage and it's like one. Okay, so I hope that you get the understanding. Okay. So yeah, that's what I was talking about, the things like how we see the picture quality, etc. So this is like we have a cube, which I told you like just like this. Like we have a matrix, a 3D matrix. One is for the values of R, one is for the values of G, one is for the values of B. And depending on the quality of the monitor, depending on the technology, there can be more matrices for different colors and different states. And below you see is a CRT, or I should say not CR, not CRT, it should be color, like color images, like how we see color images. You know that there used to be black and white TVs. So black and white TVs were just like this. Okay. So suppose I want to show a figure of like suppose this figure I have to show. So all I need to do is first say this color as cyan, 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 cyan. This color as black, 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 black. This is as blue. This is as white. This is as white. Cyan, cyan, cyan. It's not cyan really. It's like not cyan. It's like a yellowish color. Forgive me, not yellow exactly. I don't know what shade of color is it, but just bear with me. So yeah, that's how it works. Okay, and so if I have to display a line in a pixel in a black and white monitor, all I have to do is just suppose I have to display this line, like this line on the screen. All I have to do take all values of zero, or suppose I have to draw a face. Okay, if I have to draw a face like this, what I will do, see the better quality, if you need the better quality, you will need to have more rows and columns, if you know what I mean. and I can create a other different video on this because I think we are debating on our topic why quantum computers we need. So yeah, okay. So this is one, 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 this is one. So all we get a circular face, and to give the eyes, maybe we need to move bigger circular face. So this is one. This is for the face, this is for the eyes, and this is for the ear. So yeah, you can see that it looks horrible because we have less number of rows and less number of columns. But in reality, we have more number of rows and more number of columns. Okay. So yeah, that's how the classical computer works. Now let us understand how the quantum computer can beat the classical computer. Well, not exactly beat it, but yeah, it has also its constraint we will get to understand about it. So yeah, uh, so we were understanding how the quantum computer is special. Well, it has some special principles like entanglement and superposition and whatnot. Just give me a moment. Okay, perfect. So it has also special principle like entanglement and superposition. And using these principles, we get some more characteristics. Like, so suppose we have a qubit. In classical computer, we say bits. In quantum computer, we just say Q U plus bits, like qubits. Q is for quantum, you can get. So qubits. Okay, so suppose you have a bit like in binary, it's like 1010. So that's your bit. So every bit, yeah, every bit will represent only one specific state. So what I'm trying to mean is, कि suppose I have this bit. Okay, we both know that it can be only one or it can be zero. Okay, and we have to predefine it like what is it? Like we cannot keep in okay, it may be one or zero. It has to be any one. Like it can be one or it can be zero. Okay, so that's the constraint of bits. So yeah, here every bit, one bit represents one size only, or I should say n bits represent and one case only. Okay, like suppose I just told you like my name Dave can be written like just a combination of one bit or something like that. But in Cubase, suppose I have Cubase Q1, Q2, Q3, where there is no need to initialize that it has to be 1 or 0, it has to be 1 or 0, it has to be 1 or 0. It can be either 1, it can be either 0, or it can be the combination of both 1 and 0. It can be the combination of both 1 and 0. Let me pause it for a minute. Sorry for the disturbance. Yeah. So what the thing is, it can be 1, it can be 0, or it can be 1 comma 0. So suppose I have n bits. This is I have n bits like 1, 2, 3, and dot 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 n bits. Okay. So these n bits represent total 2 to power n cases. Okay. So yeah, it represents 2 to power n bits, and it's I understand it will be difficult to understand to get like for you it has to be either one or zero. How can it be both one and zero? Or how cannot be neither one or not zero? I think it would be difficult for you to understand it for right now. But believe me, after this playlist or after this foundation course, you will understand how the quantum computer is beautiful and how can it solve many problems. Okay, suppose like if you have to find what I can explain you like this. Suppose there is a maze. Yeah, okay. Suppose there is a maze and there are few entry points. Yeah, and this is closed and this, oh sorry. Yeah, this is closed. Yeah, so suppose there is a maze. I am not able to draw a perfect maze. But yeah, so this is the starting point. This is the starting point and you have to find a way in. For if custom has worked, so it will find one way and will find to try to find, it will try all the possible ways to get to the final output. Okay, but the custom computer works like it will simultaneously select all possible ways. Forgive my intrusion. Let me take a better image in the next slide. So yeah, that's the perfect way to how The perfect way to understand the difference between classical computer as well as quantum computer. So yeah. So if I have to find the way out, how will the classical computer work? If we try to find all possible cases one by one. So if we first try this case, red case, oh, and then it fails. So we backtrack and we find where was another way. So there was another way. Let me represent by this as blue color. So yeah, that is second way. And here it also failed. Now let me try third case. Third case as we have another way like this, and then it tries this case. Okay, and then another case is like, can I go with same color? No. Okay, no. So yeah, let me take as black color one. Can I? Oh yeah. So this is another case. So if we try to find all possible cases to, until it finds a way out, and you can understand how much time it will take to find the answer. So there will be, if there are n possible ways, if there are n possible ways, then we try n cases. Okay. Now what's the difference between quantum computer? How will it work? Okay. Let me take it as green color. We haven't done green color, or we have done it. Okay. First let me erase it. Oh, sorry. Okay. So yeah, yeah, first let me erase it. Okay, yeah, perfect. So इसे कट कर देना. Okay. So yeah, अगर green color से दिखाना हो तो इसमें हर बार में वो सारे possible cases, if we try all the possible cases at one time. ठीक है? So if we try this case too, if we try this case too, if we try this case too, and if we try this case too, and here's we go. Let me find the answer first. Okay, there it is. I think the answer will be like this, and this. So yeah, that's how we will find the way out, and there we will get the answer. So there we find the way out, and we get the answer. So basically, quantum computer represent all possible states simultaneously. So if I'm writing Q1, Q2, and Q3, then it will be able to represent 8 possible states at once simultaneously. 8 possible states simultaneously. Believe me, I think it will be hard for you to get it at first. It was for me to get it at first, but as much as I delve into the field of it and as much as I get into the mathematics part, believe me, if you are not a mathematics lover or if you are a mathematics lover, you will fall in love with in maths in both ways. So yeah, I'll be with you throughout this whole journey. Just don't break it. And I assure you that it will be worth it to understand the field of quantum physics, and you will get to see many good professors like Feynman, etc. So yeah, that's all for today, and we will be seeing you to next field where we will be understanding the quantum case. Like we have OR gate, AND gate, NOT gate. Similarly, quantum has X gate, C NOT gate, and Hadamard gate. We will be understanding these cases in the next lecture. Okay, comment me if there are any things you want to understand or there are any doubts or anything wrong which I've taught you here. So yeah. I'm welcome to all of this. So that's all for today. See you tomorrow.